Hi everyone, I'm Suren and I'll be doing today's presentation on an optical physics inspired CNN approach for intrinsic image decomposition. A fundamental problem in computer vision is the ability to deduce intrinsic properties of 3D objects when it's presented as a 2D image. These intrinsic properties are the reflectance, the illumination, and the shape. And in order to extract all this information from an image, an observer would in general need to have multiple views of the same object. This is because different people may perceive the same image in different ways based on their perspective. Thus, inferring these properties from a single image is often a challenging task. IID, or intrinsic image decomposition, is a problem where we try to decompose an image into its constituents so that we can get a better understanding of its properties. In this work, our objective is to decompose an image into two components, namely the reflections and the shading. The first way to decompose an image is through supervised techniques, which requires both the input and the desired output. In this case, it's going to be the shading and the reflectance, and this is impractical due to the lack of large data sets with ground truth. Alternatively, IID can also be done in an unsupervised manner. However, this becomes even more challenging since there is no ground truth. Therefore, in general, there is a lack of unsupervised approaches. Furthermore, the existing unsupervised approaches often fail to provide consistently good results under different environmental conditions, and sometimes they may even fail to consider many physics-based attributes. However, there are certain properties of these components, like for example, the reflectance, it contains the light information, the color information, which is light invariant, whereas the shading, it contains the information about shape, the normal and contours, and all other illumination-dependent information. Therefore, by formulating and analyzing these properties of an image, we could improve the efficacy of our decomposed outputs. Based on this idea, we propose a novel unsupervised IID technique, which was inspired by optical physics, and it's capable of decomposing a wide variety of images under different conditions. The first step needed to decompose an image is to understand its properties. We begin with the Fong's model as the mathematical model to derive these physics-based properties. So the Fong's model describes the intensity of a pixel as a combination of three constituents, namely the ambient light intensity, the diffuse light intensity, and the specular light components. So this can be mathematically given as the addition of three components, where the first component is the ambient light component, the second is a diffuse light component, and the third one is the specular light component. You could find more specific information about this on our paper. So moving on, next we try to simplify the Fong's model. First, by considering a narrow band lambda c, we could remove the integration operation. Then we make certain assumptions. The first assumption is that the ambient light is constant, and as such, we can ignore the first term. Next, we assume that there is only one light source for simplicity. Third, we consider that the circular term to be negligible, and we ignore it. Finally, we could also remove the coefficient kd. Since we'll be working with logarithmic ratios in this work, for simplicity, we'll remove most of the constants as at this stage itself. So finally, based on all these assumptions, we can obtain a more simplified equation. Note that now we have two separate components: the reflectance, which is only given by the first term, and the shading, which is given as a combination of the rest of the terms. So next, the equation which is given as a product must be decomposed to separate each of these components. In order to do this, we first derive the three following parameters, which provide additional information about the image and thereby gives us better results. The first parameter is the reflectance ratio gradient, or the RRG, which is used to identify the boundaries of the reflectance. The RAM, or the reflectance approximation map, it helps us make an approximation of the reflectance. And finally, the shading gradient helps us identify the shading component. We'll go through these parameters one by one. So first, for the RRG, we begin with the simplified Fong's model. First, we consider the log ratio between the intensities of two wavelengths for a single pixel. So this is given by the first equation that you see over here. Next, if we consider the gradient, we could assume that the intensity ID for two adjacent pixels are the same. And thereby, the gradient can be even simplified as shown in the second equation. Note that this value only depends on the reflectance, and it's equal to the logarithmic gradient of the ratio between two reflectance components. Therefore, we call it RRG. And the RRG of the reflectance is equal to the RRG of the image pixel intensity. We use this specific property to derive our first loss component. Next, we approximate the reflectance through the RAM. For this, we consider two wavelengths, and if they have equal intensities, then we know that the log ratio is 0. However, if one wavelength is dominant compared to the other, then this ratio will be high. Based on this idea, we create 3-channel image matrix called the reflectance approximation map. As shown, the RAM of a channel, in this case, it's a red one, is given by the average of the ratios of the red channel with respect to the green and the blue channels. So in this case, if the red channel is dominant, its RAM will be high, and if not, it will be low. Note that a high RAM value means that the reflectance is more likely to be dominated by that particular channel. And we clip this value between 0 and 1 so that it's easy to interpret when we create the corresponding loss function. Finally, for the shading gradient map, we consider the natural logarithmic value of the intensity, which is given by this term kappa. So now if two neighboring pixels have the same reflectance, we can see that the gradients of this value is independent of both the reflectance and the illumination. This is shown in the first equation. We use this property to define the shading gradient. This SG value is equal to the log gradient of the image if two adjacent pixels have the same intensity value, and if not, we define it to be 0. We check if two adjacent pixels have the same value by constructing something called an RRG map, which is given in the third equation. The value of the RRG filter map will be low if the adjacent pixels are similar, since the gradient is lower, and it will be high if not. So the visual representation of these 3 parameters are shown in here. You can see that the first figure, the RRG, it highlights the borders of the object. The second figure, the RAM, it shows more of the dominant colors and it amplifies them. And finally, the shading gradient, it highlights the rate of change of normal when the reflectance stays smooth. Next, we come to the decomposition. To decompose an image, we use a CNN model which was trained in an unsupervised manner using our proposed loss function. First, for the CNN architecture, the input is a 3-channel image. It is first concatenated with the maximum intensity value of the RGB. Then the concatenated data is passed through 5 convolution blocks. After performing one more convolution and activation operation, 2 copies are made of this output. The first copy, it's concatenated with the image and then passed through a couple of convolution and activation layers to obtain a 3-channel reflectance map. Whereas the second copy is concatenated to both I and max I, and then passed through similar convolution blocks to obtain a single channel shading. The exact specifications of these filters and the activation can be referred from our work. So next, we move on to the training. The CNN was trained using this proposed loss function, which is given as the weighted average value of 5 components. These are the reconstruction loss, the shading smoothness loss, the reflectance ratio gradient loss or the RRG loss. Then we have the RAM loss and the shading gradient loss. So we'll go through them one by one. The first component is the RRG loss. You may recall that the RRG of the image should be equal to the RRG of reflectance as shown in this figure. So this component ensures that by taking the absolute difference between these 2 RRG values. Next is the RM loss. It ensures that the dominant wavelength in the reflectance is same as the one in the image. So as you see in this figure, if the red is significant at a certain point of the RAM, the reflectance should be predominantly a shade of red. The RAM loss component enforces this by the given formula. It ensures that when the RAM is activated, as in when the RAM value is high for a particular wave, then the corresponding wavelength should also have a high reflectance value. Next, we have the shading gradient. This ensures shading gradient loss. This ensures that when the reflectance is smooth, the gradient of the shading and the image are similar. That is, like when the color stays the same, all other lighting dependent features must be transferred to the shading component. This is done by the following equation, which is similar to the last one. As in when the SG is activated, this component makes sure that the shading component varies in the same way as the image. The fourth component is the reconstruction loss, which is commonly used in many image decomposition models. It ensures that the original image can be constructed back again from the decomposed R and S components. In this case, it's through pixel-wise multiplication. The fifth and the final component is the shading smoothness loss. So when the RRG is low, it means that the image does not have any boundaries at this point. And as such, the shading should also be smooth. Therefore, by considering the gradient of the shading component in this equation, we can ensure that the shading is smooth whenever the RRG is low. Finally, we train the model, the CNN model, using the proposed loss function and the following parameters. For training and validation, we use the LOL data set. Since it has no ground truth, it's appropriate for the study. We used 485 images for training and 15 for validation. For testing, we used the MIT data set, which is ideal in this scenario since it has a ground truth for both the shading and the reflectance. You should refer more information about the training process in our paper. So next, moving on to the results. So this figure shows the visual outputs obtained using 3 unsupervised techniques and our proposed model. In this specific image, we can see that the proposed model extracts the reflectance as well as the shading components quite well and provides visually pleasing output in comparison to other works. For instance, the second image, it does not provide most of the reflectance information, as in it's undersaturated, whereas the reflectance of the third one is a bit oversaturated. As for the shading, a major issue in shading most of the models is the color leakage issue, where some of the color information is leaked from the reflectance to the shading. So in this case, ideally the shading should only not have any blue lines. It should only be in the reflectance. You can see that our proposed model actually extracts most of the color information and into the reflectance, leaving some of them into the shading. On the other hand, the first and the third image suffers most from color leakage issue, and as a result, many of the blue lines are transferred to the shading component, as you can see from the figure. But despite all this observation, the proposed model does not always give the most visually pleasing output. For example, in this case, the reflectance is highly saturated, and as a result, it fails to transfer most of the lighting information to the shading. So to do an objective comparison, we move on to numerical metrics. For numerical comparison, we use 4 metrics. The first one is a root mean square error, and a low RMSE value indicates a better performance. Then we consider the peak to signal ratio, and a higher PSNR indicates better results. The structural similarity index and the naturalness image quality indicators, these are 2 metrics that quantify the quality of an image, and this usually needs to be high as well. The metrics on the validation set for 15 LOL images, it's shown in the table, where the best value is bolded and the next one is underlined. We can see that the proposed model often provides the best or the second best performance in terms of numerical metrics. Similarly, the numerical metrics on the test sets of 20 MIT images are shown here. Since MIT dataset has the ground truth in addition to the images, we also consider the RMSE and PSNR of the reflectance and the shading for evaluation. Again, the proposed model often comes as the best or the second best. So we can conclude that the proposed model consistently outperforms other unsupervised techniques and on average provides better results on a wide variety of images. So to summarize our work, we proposed an IID technique based on the Fong's model. We created a set of matrices to extract meaningful information from these images. We proposed a CNN model and an optical physics-inspired loss function to train said model. Finally, through visual and numerical metrics, we showed that the proposed model consistently outperforms other unsupervised models. That's all I have from my presentation. Thank you for your time and have a pleasant day.